We'll now continue talking about the effect of dilute solutions of non-volatile solutes. So what I want to do here, though, is to talk about some of the considerations that might affect their solubility. And I'm specifying non-volatile solutes because I want to continue the conversation that we began in the previous lesson so that we can begin to understand how these differ from the more volatile, volatile liquid-liquid solution type cases that we've looked at before. Okay, so what are we talking about when we're talking about these non-volatile solutions and their thermodynamics? We're talking about a process that basically has some substance that is going from a solid state into a solution phase. All right, so that's the essence of the process. Now, we could begin to treat this thermodynamically by, for example, talking about the chemical potential of this, and I'm going to use the subscript 2 to indicate this is the solute that we're talking about. In the solid phase, this chemical potential might be given by some expression that looks like this. Okay, where again this is referring to a solid phase. But since we know that the chemical activity of a pure solid is going to be generally taken to be 1, this term is going to disappear, and this will simply be equal to the reference chemical activity for the solid. For the solution, we'll have a similar but a little bit different arrangement. Again, we'll have a reference chemical potential for the solution, and we'll have RT log of its chemical activity. Now, I'll remind you that chemical activity in this case is in essence the concentration, if you will, of the solute. Okay, I was about to say the mole fraction, but more generally speaking, it is the concentration. So the whole idea that we want to get after is when we achieve an equilibrium here, in other words, when these two are at thermal equilibrium, what can we expect for the value of this chemical activity? Now, this is going to be something that is a function of temperature, so what we're really driving at here is we want to know something about the temperature dependence of A. I should say A2. All right, so if we're at chemical equilibrium, for thermal equilibrium, then these two quantities must be equal to one another. That's what an equilibrium really is defined as thermodynamically, that we must have these two in balance with one another so that there's no thermodynamic force that pushes this process one direction or the other. All right, so if I were to subtract these two equations from one another, what I might have is something that looks like this. Actually, I'm going to take the top one and subtract it from the bottom one. So the bottom one, I'll have mu2 solution minus mu2 solid, which is just these two things, which we've agreed is 0 at thermal equilibrium. And then for the right-hand side, I'm going to have mu2 reference solution minus mu2 reference for solid plus RT log of A2. And I'm going to stop writing solution since the only activity we have here is the activity of the solution. All right, now if I were to rearrange this equation a little bit, I could basically capture the activity on one side. So I'm going to write this as log of the activity is equal to, and I'm going to move this stuff to the other side. I'll put a negative sign in front of it, mu2 0 solution minus mu2 0 solid divided by RT. All right, and it begins to feel like we're getting something where we can understand something about the temperature dependence, although when we talk about this thermal equilibrium, we're really talking about something that's occurring at a constant temperature. So I need to be mindful that this is an equation that is for a fixed temperature. And what I'm really interested in is how this varies with temperature, because that's going to give us maybe a deeper understanding about solubility as a function of temperature. So how can we do that? Well, one way is we might recognize that chemical potential, and let me write this separately over here, chemical potential is essentially a molar Gibbs energy. Okay, so if we have a molar Gibbs energy here, and I'm taking the change here, what does this change involve? Well, I've got the Gibbs energy on this side, on the solution side, and the Gibbs energy on the solid side. So the net change for this process is a change in solvation. So I could write this as negative delta G molar for solvation over RT. Okay, and I'm using this tag here simply to indicate that this is the particular process, this one where I'm going from a solid to a solution phase A as the one that I'm dealing with. Now, how might we write this delta G solvation? Well, for a fixed temperature, delta G solvation might be equal to delta H solvation, molar quantity, minus T delta S solvation. All right, so how are these things going to affect delta G? Well, delta S, I think, is pretty clear. Whenever we're taking something and mixing together, we're providing access to a lot more microstates. So in general, this one is going to be greater than 0 for this solvation process. We are basically creating a space in which this system has many more states available to it. Can we say the same about delta H? Well, let's break delta H down and talk about it in terms of the components that contribute to delta H. So we've got 3 different ones, and we're going to talk about the interactions between 2 solute particles, the interactions between solute particle and solvent particle, and the interaction between 2 solvent particles. All right, now in the first case, in order to get this thing to dissolve, we're going to have to break those interactions. The same is going to be true for the solvent-solvent interactions. We're going to have to push them apart in order to create space for these solute molecules to be in there. So I'm using the term break, but you can take this rather euphemistically. All right, the one that we're going to form, though, we're going to form new interactions between the solute and the solvent. So these are going to be a form interaction. All right, so in terms of enthalpy changes, we would expect that the enthalpy change for this would be greater than 0, and the same would be true for the enthalpy change for this. But the enthalpy change for forming new interactions is going to release energy. It's going to be exothermic. So this is endothermic, this is endothermic, and this one is exothermic. All right, at the end of the day, we cannot necessarily say that all solvation processes are going to be endothermic or all will be exothermic, because we don't necessarily know before examining the substances, we don't know what the balance is going to be between these 3 contributions for enthalpy. So I'm going to leave that as sort of an open question. All right, but in this particular case, we'll program in something that will be an approximation, but will at least give us an ability to generate some handle on it. Okay, so now I have an expression that tells me something about log related to Gibbs energy. How can I get something that tells me more about the temperature dependence? This is at a fixed temperature. Well, I could take the derivative of both sides with respect to temperature. So in one case, I'd be taking the derivative of log of this activity, and in the other case, I would be taking the derivative of this quantity, negative delta G solvation over RT. Okay, well, the R part is just a constant, so in fact we could bring it outside of this, and I'll end up with a temperature derivative. I'll write this like this: a temperature derivative of delta G, and I should put the bar over that because these are molar entropy, molar energies, over T. But this should look familiar to us. Back in Module 3, we talked about taking the temperature derivative of delta G over T, and it led to something that we identified as the, well, I should put Gibbs first, Gibbs-Helmholtz equation. All right, and when we take this derivative of G, what we end up with is, I should say it's a negative sign in front of this, negative delta H molar of solvation over T squared. So now if I insert this result in for taking this derivative, I'll end up with a differential equation that will look something like this. And I can bring the dt over here so that I've got two perfect differentials. So let me do that in sort of a sloppy way here. So I'll then have a differential equation that I can readily integrate. And when I do, I'll end up with a final result that looks something like this. I'll have log of A2, and I'll indicate this is as a function of temperature, is equal to the delta H solvation molar quantity over R, and I'll have 1 over T reference minus 1 over T. And this T reference, let's talk about that briefly. First of all, I don't know what this is necessarily off the top, but if we focus on the solute and what's happening there, and just say that everything else with the solvent, because it's in the great majority, is going to be a wash, that is to say it's not going to matter as much, we might say that this process is akin to a melting process. So in other words, we could, instead of using delta H solvation, use delta H of fusion. And for this reference temperature, we might use the fusion temperature of A. And in fact, when we substitute these things in here, we can then begin to get a handle on how A changes with temperature. It's an approximation, because I can tell you that this is a very rough approximation that we've suggested here. But this is the very one that you see being touted, if you will, in one of the reading sections in one of the videos. And it gives us a way of estimating a solubility, because this activity now is related to a concentration, and that concentration tells us how soluble the solute will be in the solvent. All right, so this has been a long way of trying to introduce to you some of the factors that influence the thermodynamics of this solubility process, while unfortunately not getting to a conclusion, at least suggesting how one might approximate or estimate the result that you want.